is Roger Green, host of the Surfing the NASH Tsunami podcast. We are offering 3 conversations from episode 42, which focused on the role fibroblast growth factors, or FGFs, play in the body and how FGF agents might fare as NASH pharmacotherapy once approved. The conversations do not follow the order of the episode itself. This conversation focuses on FGF as medicine. Stephen Harrison discusses the results from efruxifermin clinical trials to date. Arun Sanyal discusses why one FGF agent might be more promising than other. And both agree with the implication of Roger Green's question about whether these are an extremely promising class of agents. Arun and Stephen are brilliant at explaining complex concepts simply. Listen twice or 3 times if you must, but you will walk away with knowledge you did not start with. So sit back, listen, enjoy, learn, and when you're done, join the discussion on our LinkedIn and Facebook discussion groups.
Arun Sanyal.
The FGFs are a family of cytokines. Cytokines mean that they're being produced by different cells. These are chemicals being released. And we classify FGFs based on whether they act on the same cell that produces them. Those are intracrine FGFs. Then there are paracrine FGFs, which work on adjacent cells. And then there are endocrine FGFs, which are released into blood and then carried to distant sites and act on distant organs. So here, what we're talking about are the endocrine FGFs. And so in the endocrine FGFs, you have FGF21 and 19 are 2 of the principal endocrine FGFs. The principal difference between FGF21 and FGF19 from a clinical point of view relates to the type of receptors they bind. So for FGFs to do anything, they have to bind to their receptor on cells. Now, they require 2 receptors. One's called beta-klotho, and the other one is called FGF receptor. Now, for FGF21 to work, it has to bind FGF receptor 1 as a minimal requirement along with beta-klotho. And actually, the Merck compound, the NGM313, is a FGF receptor 1 beta-klotho analog. Now, the other FGF21s can bind not only FGF1 but also FGF2 and 3 to varying degrees, but they do not bind to FGF receptor 4. So that's where FGF19 comes in. FGF19 can bind to FGF receptor 4. That's what principally distinguishes the FGF21 biology from FGF19 biology. The second principal difference is that the FGF21 is principally a hepatokine. That is, it is produced in the liver and can be released. It can also be made in adipose tissue and it can be released into circulation. FGF19, on the other hand, is released from the intestine after bile acids bind to a receptor called FXR in the intestine, and the largest amount of FGF19 in the body comes from the intestine and is released into the intestinal outflow, that is the circulatory outflow. And this is important because this brings it straight to the liver. The liver is the first organ that sees all of the blood that is draining the intestine because that's where it carries the nutrients. And then FGF19 has a principal effect on the liver where it has the FGF receptor 4, which gives it the hepatic specificity, whereas FGF21, which binds mainly to 1, 2, and 3, along with beta-klotho, can not only affect the liver, but can affect fatty tissue, can affect bones, can affect and also very importantly, the brain. So, Roger, I think that sort of, unless you want to know more, I can keep going, but I think that's a good place to start.
Roger Green.
Stephen, if you wanted to amplify, and Louise, let me do Stephen first. Anything you want to amplify on that?
Stephen Harrison.
I think that was terrific.
I thought it was
just
great.
A nice summary. Just backing up a little bit, it's important for our audience to realize how fat gets in the liver. I don't think we've really been through that much on the podcast. And I think it's apropos to this discussion. So majority of fat coming into the liver is happening because of sick adipocytes. Sick adipocytes undergoing lipolysis, releasing free fatty acids that get taken up by the liver predominantly. And second most common is de novo lipogenesis, and third most common is through nutrition. And that's relevant to this discussion on FGF21, particularly, and FGF19, particularly through the binding of FGFR1C, beta-klotho. So this idea that we're binding the FGF1 receptor, its activity is in the adipocyte predominantly. So by modulating that, you can can theoretically have a major impact on fat inside the liver. And we see that FGF19 aldafermin binds 1 and 4, whereas most of the FGF21s bind 1 and then to variable degrees 2 and 3, which maybe, Arun, you can talk to 2 and 3 a little bit about maybe where they're predominantly located and what their effects are. That actually is one of the bigger differences between why there are potentially variances in how these FGF21s work a little bit, how effective, how potent they are. But quite frankly, the major impact of liver fat content reduction, specifically how we saw absolute reductions of 12 to 14% with efruxifermin in the Balance paper, was it, I think, impacted mainly through its binding to the 1C receptor. So I just wanted to throw that out there as just a little added piece of information.
Arun, you want to comment on the difference between 2, 3, and 4 Stephen suggested?
Yeah, so 3 and 2 are expressed in other organs. There's not a whole lot known. 2 is not very well characterized from a pharmacology point of view, but the 3 is also expressed in the brain. So, for example, if you bind to 1 and 3 in the brain, actually has been shown to reduce your desire for sweet food and increase your protein intake. So, your choice of food, it can affect what you crave and what you desire to eat, for example. So, but I think from a biological perspective, 1 is really important because of its expression in adipose tissue, as Stephen mentioned. And what it does there is that it turns on this secondary hormone that the fat tissue makes called adiponectin. Now, adiponectin is critically associated with maintaining insulin sensitivity. So it keeps the tissue sensitive to insulin. And then when your adiponectin levels normally fall in obesity and in insulin-resistant states, then your cells are no longer responding to insulin. So by increasing adiponectin, it improves insulin sensitivity. When you become more sensitive to insulin, for any given level of insulin, you're more likely to drive the fat into the fat tissue rather than out of the fat tissue. Now, you may say that doesn't make any sense. In a disease with obesity, why would you want to do that? It is because when you drive fat out of the adipose tissue, the fat has to go somewhere. And one of the big metabolic defects that occurs is that you're unable to oxidize that fat appropriately. So you can't burn it in your muscles appropriately. So the liver is the next organ that accepts fat. And so you end up delivering a very large amount of fat to the liver, which then creates a metabolic stress on the liver and triggers the sequence of events that we recognize as NASH. So this also opens up the possibility that if you could modulate this metabolic capacity to burn fat in muscle tissue in the fasted state, you might have another mechanism by which you could reduce delivery of excess fat to the liver. Now, the development of insulin resistance in the liver has a second effect through the muscle, because when you become insulin resistant in the muscle, you not only are unable to burn that excess fat, but you also are unable to take up glucose from the circulation. Normally, when you eat a sugar load, that extra sugar is cleared from your blood by muscle. And if you're unable to do that, all that extra sugar is delivered to the liver, and sugar is the substrate for de novo lipogenesis. So you get a double whammy. First, you're getting lots of fat delivered, and number 2, you get a lot of sugar delivered to the liver. The third clinical implication of this is that when you are moving fat from your adipose tissue masses into the circulation, but you cannot burn it and you're delivering it to the liver, at a certain point, you saturate the liver's ability to take it up, but a lot of that extra fat returns to the fat tissue. So the patient is unable to mobilize that fat and unable to lose weight. So they'll tell you, I'm trying to exercise, but I'm not losing weight. How often have we heard that? And it's a common mistake for physicians to then claim that the patient is lying, they're being lazy. But the truth is, if you're really metabolically resistant to the actions of insulin, that leads to this inability to mobilize fat, because the fat that does come out of the fat stores cannot be burned, so it goes back into the fat tissue or it goes into the liver to create fatty liver disease.
Yeah, that's fascinating. I just wanted one thing to add to that, since you were speaking about adiponectin. Juan Frias presented at the recent ADA some follow-up data from the Balance trial, looking specifically specifically at adiponectin. And just the conclusions of that, I'm pulling his last slide up now. Increases in adiponectin correlated strongly with improvements in lipid and lipoprotein profiles, as well as markers of insulin sensitivity and glucose metabolism, and reduction in biomarkers of liver cell injury and hepatocyte stress, as well as liver fibrosis. So that speaks to your point a bit more directly.
Yeah. And Stephen, as you know, I've been a great protagonist from day one that the best way to reduce scarring in the liver is to treat the root cause. And if the root cause is delivery of excess sugar and poisonous fats to the liver, reducing those is the best way to reduce everything that happens downstream. But the FGF21s have an additional effect that is directly in the liver. When you deliver excess fat to the liver, you trigger something called ER stress or stress to the endoplasmic reticulum, which causes an unfolded protein response. FGF21 can actually be produced as a consequence of unfolded protein response, but it basically impacts many of the pathways that drive inflammation and oxidative stress. So there is yet another layer of direct effects within the liver beyond what you're seeing in the adipose tissue, etc., that contribute to the beneficial effects of FGF21s.
And now, back to Roger.
We hope you've enjoyed this recording. If you have any questions or comments about the content of this conversation or the entire episode, please send an email to questions@surfingnash.com. We will be back next Wednesday, August 25th, when Jorn Schattenberg joins us to discuss cirrhosis, the disease, and prospects for drug therapy. I hope you'll join us then. Until then, stay safe, surf on, and see you on the podcast. Bye-bye now.